We're talking about reaching for the stars, not with chemical fire and thrust, but with, well, essentially a piece of string that runs 100,000 kilometers into the sky.
By 1891, state-of-the-art presses were producing 90,000 four-page sheets per hour.
Okay, let's put that entire journey into one final perspective. Hand copying. A few pages per day. The original Gutenberg press. 240 impressions per hour.
Koenig's first steam press jumped that to 1,100 impressions per hour in 1814.
And by 1891, the rotary press was achieving 90,000 four-page sheets per hour.
That is a speed increase that truly restructured human civilization.
And that's the moment.
What moment?
The moment heresy stops being just a spiritual danger and becomes an act of treason against the Roman state, a precedent that would last for centuries. Welcome to the Deep Dive, the place where we take the world's most audacious concepts, grab the blueprints, and really figure out if they're on the cusp of a breakthrough, or if they're just firmly in the realm of perpetual science fiction.
And today's concept is a big one.
It is. Today, we are attempting to replace the rocket entirely. We're talking about reaching for the stars, not with chemical fire and thrust, but with, well, essentially a piece of string that runs 100,000 kilometers into the sky.
That's right. We're tackling what may be the greatest, most challenging infrastructure project ever conceived, the space elevator.
Sometimes called the skyhook.
Right.
Or even more dramatically, a star ladder.
A star ladder or an orbital lift, yeah. It's a structure that would just fundamentally redefine our entire relationship with gravity and space access itself.
The idea, the mythology of it is just so captivating. An actual fixed line connecting the surface of the Earth directly to a stable point in orbit. It promises reusable, predictable, and incredibly cheap access to space.
That's the dream.
And our mission today is to unpack the reality of that dream. We're going to dive deep into the, frankly, bizarre physics that keeps the whole thing standing up, the architecture you'd need to build it, and the immense, currently unsolved material science hurdles this project faces.
So for anyone who wants a serious, a comprehensive understanding of how this could transform space access, if it can be built at all, this is your essential shortcut.
Okay, so to start, let's define exactly what we're talking about. The modern tensile design of the space elevator.
Right. It's an Earth-based system with 4 essential components, and they all have to work in perfect concert. First, you need a cable, a tether or ribbon that's anchored somewhere near the equator.
And that's crucial, the equator part. You need that maximum rotational assist from the Earth.
Absolutely. Then the second critical component is that this cable can't just stop at the edge of space.
Right, it has to keep going way, way out.
It has to extend far beyond what we call geostationary orbit, or GEO. That's at an altitude of 35,786 kilometers.
A lofty altitude.
Very. And third, at that upper end, far out in space, you need a substantial mass, the counterweight.
And that counterweight is really the linchpin of the whole thing, isn't it? It's not just a weight sitting there.
Not at all. It's the rotational energy of that weight that holds the entire system up. It's the anchor that keeps the cable taut against Earth's gravity.
So it's whipping around with the Earth's rotation, and that inertia generates this massive tension.
Precisely. And then fourth, you need the mechanical transport. The climbers, sometimes called crawlers, that move cargo and people up and down that stationary cable.
And the core benefit, the thing that drives all the research and all the investment.
It's transformative. You get direct, high-volume travel between the surface and orbit without needing massive, repetitive, and hugely expensive chemical rocket launches. It makes space access feel less like this heroic undertaking and more like, well, logistics.
Like running a freight train to the stars. Now, this might sound like a very new concept, something driven by 21st century material science, but the audacious dream of connecting Earth and space with a stationary structure actually began well over a century ago.
Way back in Tsarist Russia, actually.
Yeah. We have to start with Konstantin Tsiolkovsky in 1895. He's known as the father of rocketry, and in his collection Dreams of Earth and Sky, he envisioned what he called a massive Sky ladder.
A sky ladder to overcome gravity. But here's where the history gets really interesting and often a little confused. Tsiolkovsky's original concept was not the modern tensile design we're talking about today.
It was a tower, correct, a compression structure.
Exactly. He envisioned a colossal aerial mast, a tower built from the ground up, held in place by its own structural rigidity, like a skyscraper, but reaching 100 kilometers or more.
Which was, ultimately deemed impossible.
Yeah, completely impossible. The materials at the time and even now just couldn't do it. To hold up the mass of the tower above it, the base would need to be impossibly wide. It would just collapse under its own colossal weight long before it got anywhere near orbit.
So the idea of a fixed structure was sound, but the method was impossible until someone, flipped the whole concept on its head.
And that's exactly what happened independently in 1960. A Russian scientist named Yuri Artsutinov developed what he called a cosmic railway.
His idea was to build down, not up.
Precisely. Launch a satellite into geostationary orbit first, and then deploy a cable downwards using the centrifugal force of a counterweight above to keep the cable taut. This tensile design, held up by tension from space, is the foundational design we use today.
And the idea eventually made its way to the West, and that's when it got some critical design refinements in the U.S.
Right, that momentum started pretty quickly. In 1966, John O. Isaacs and his team introduced the skyhook concept. They really hammered home the importance of extending the cable downward from a GEO satellite.
But the really rigorous engineering analysis, the stuff we rely on today, was solidified about a decade later with Jerome Pearson.
Pearson is incredibly important. He started researching this seriously in 1975. He was an engineer for NASA and the Air Force Research Lab, and he developed the detailed design for the orbital tower.
And his big contribution was figuring out the actual geometry of the cable itself, which is a highly complex calculation.
It is. He calculated that because of the varying forces of gravity and centrifugal pull, the cable would need to be thickest right at GEO altitude.
Where the tension is the greatest.
Absolutely, where those opposing forces are at their maximum. And then it would have to taper dramatically toward both ends, toward the surface and toward the counterweight. It was a crucial detail for minimizing the total mass of the system.
And his calculations for the counterweight really showed just how massive this thing would have to be.
They really did. He proposed a massive counterweight, potentially extending the cable structure to an incredible 144,000 kilometers.
89,000 miles. That's nearly halfway to the moon.
It's an immense distance. And he also started analyzing all the external forces, like the moon's gravity trying to pull on the structure and things like wind and lightning near the base. He treated it like a real dynamic system.
It feels like Pearson made the leap from a theoretical curiosity to a detailed engineering problem.
He did, and that's where the concept truly entered the cultural sphere. Pearson's findings directly influenced Arthur C. Clarke.
For his 1979 novel, The Fountains of Paradise.
Exactly. That novel, and another one, Charles Sheffield's The Web Between the Worlds, introduced the space elevator to a massive global audience. It went from obscure engineering papers to this plausible, aspirational technology.
And that spurred renewed interest, leading to a NASA conference in 1999 on this very topic.
Right, but that initial 2000 NASA report basically concluded it couldn't be built for at least 50 years. The materials were the main problem.
But then the assessment shifted pretty dramatically in the early 21st century.
It did, because of the tantalizing promise of nanomaterials, specifically carbon nanotubes or CNTs.
And Dr. B.C. Edwards became a key proponent around that time.
He did. He proposed a detailed design using a 100,000-kilometer-long paper-thin ribbon made of a carbon nanotube composite.
His work was incredibly comprehensive, detailing everything from the climbers to the anchor systems, including this revolutionary idea of a mobile oceanic anchor.
Yeah, that was a huge step forward for safety, maneuvering the anchor to avoid things like hurricanes or lightning strikes. His work really helped transition the elevator from a distant future concept into a serious near-future design goal.
Which led to some high-profile commitments. Japan's Obayashi Corporation announced they aimed to build one by 2050. We've seen miniature elevator experiments on CubeSats. Even Google X took a serious run at it.
Right. And the current position from the International Academy of Astronautics is one of qualified optimism. They think it's feasible if material science can deliver that necessary fiber. That remains the single critical hurdle.
Okay, so let's unpack this. Before we even get to that material hurdle, we need to understand the underlying physics. The whole thing sounds deceptively simple. A cable and a weight. But the dynamics holding it all together are where it gets really interesting. How does a massive cable stay upright?
The stability of the space elevator relies on a really elegant and precise balance between two fundamental opposing forces.
You've got gravity, which is pretty intuitive. It's pulling everything down toward Earth's center.
Right. And that force gets weaker the further you go out. The counteracting force is the upward centrifugal pseudoforce, or, what's often just described as inertia from the system's rotation.
So everything, the cable, the counterweight, the climbers, is rotating with the Earth.
At the same angular velocity, so they all possess immense inertia. The counterweight, way out there, is constantly trying to fly outward in a straight line, but the cable holds it back.
Treating that immense tension.
Exactly. And that upward centrifugal force is dramatically stronger the further you get from Earth's center.
So you have downward gravity, which dominates close to the surface, and upward inertia, which dominates way out in space. They have to find a sweet spot.
And that sweet spot is the essential pivot point for the whole system. The geosynchronous equatorial orbit, GEO, at 35,786 kilometers up.
That's the point where the two forces are perfectly balanced.
Perfectly balanced. The downward pull of gravity and the upward centrifugal force are equal. Any object fixed to the cable at that exact point puts zero net weight or stress on the cable.
And it's what happens above and below GEO that makes the whole system work.
That's the structural genius of it. Above GEO, the upward centrifugal force is stronger than the now diminished gravity. So the counterweight and everything up there is pulling upward on the cable, generating that immense tension that keeps the whole thing vertical.
Like a giant guitar string pulled tight from space.
A perfect analogy. And below GEO, gravity is stronger, pulling objects downward, but that force is completely opposed by the tension from above.
Which leads to this really interesting concept of the apparent gravitational field. Since you're connected to the cable, you're not in free fall. You're feeling the net force of these two opposites.
That's a perfect way to put it. The apparent gravitational field is just the net force you feel. It's basically the downward gravity minus the upward centrifugal force. And it tells you which way you'd accelerate if you let go of the cable.
So if I'm a payload climber and I'm ascending below GEO?
Below GEO, gravity is stronger, so the apparent gravity pulls you downward toward the anchor point. If you let go, you'd initially accelerate down the cable.
But you'd also start to deflect eastward, right?
Yes, because you're rotating with the Earth. You'd seek a lower, slower orbit, which appears as an eastward deflection.
And then once you cross that GEO pivot point, everything flips.
Precisely. Above GEO, the centrifugal force is stronger. The apparent gravity now pulls you upward toward the counterweight. If you let go of the cable up there, you'd accelerate upward along the cable and then deflect westward as you entered a higher orbit.
So it becomes a kind of mechanical slingshot. You can launch payloads into deep space just by letting them go at the right height.
Which is one of its most powerful applications. No rocket propulsion needed after the ascent.
Okay, but if the Earth is rotating and you have these massive climbers, maybe 20 tons of cargo, moving up and down, how does that affect the rotation of the planet itself?
It does. This is the challenge of angular momentum transfer, which is driven by the Coriolis effect.
So as a climber goes up, it's moving from a point of lower horizontal speed near the surface to much higher horizontal speed near GEO. It has to gain that speed from somewhere.
And it draws that speed directly from the Earth elevator system. The climber essentially drags westward on the cable as it climbs. And this force, this Coriolis force, translates to an infinitesimal slowdown, a tiny decrease in Earth's rotation speed.
An infinitesimal slowdown of the planet every time a cargo ship goes up. So conversely, descending payloads must give that momentum back.
Correct. As they descend, they shed that horizontal speed, and the momentum is absorbed by the cable and transferred back to the Earth, slightly speeding it up.
So if you have symmetrical traffic, the net effect is zero.
Over time, yes. But what if the traffic isn't symmetrical? What if you're constantly lifting thousands of tons to build space stations and nothing is coming down?
Then the cable would start to lean.
It would lean slightly westward, yes, because of the continuous drag from the ascenders pulling it out of perfect vertical alignment. But here's the saving grace of the design.
The counterweight pulls it back.
The immense centrifugal force from that massive counterweight is constantly trying to pull the entire system back to the vertical orientation, just like a giant pendulum. So the cable is never perfectly still. It's always oscillating, always correcting itself.
Which means you have to manage those oscillations very carefully.
You absolutely do. You have to pace the climbers to keep that pendulum-like motion under control. Uncontrolled oscillation could drastically increase the stress on the cable, and you can imagine what would happen then.
A catastrophic failure. The physics are stunningly elegant, but they also show how close to the limit the system operates. And it all relies entirely on one thing.
A cable that can withstand these forces and not just snap.
And that is the absolute single biggest hurdle. It has been since the concept was first refined. The number one challenge is material science.
Specifically, the need for an extremely high strength-to-weight ratio. We call it specific strength.
And why is that ratio, and not just pure strength, the deciding factor?
Because the material has to be strong enough to hold up its own weight all the way to GEO, 35,786 kilometers up. If a material is incredibly strong but also incredibly dense, like a thick steel rod, it will just break under its own dead weight long before it even gets out of the atmosphere.
We need something that's both light and ridiculously strong.
And at the same time, yeah. And if you look at conventional materials, they're just shockingly inadequate.
What are the breaking lengths we're dealing with today?
Well, breaking length is the maximum length of a material that can support its own weight. For things like titanium, steel, aluminum alloys, you're talking 20 to 30 kilometers. That's it.
Modern fibers like Kevlar are better.
A bit better, yeah, 100 to 400 kilometers. But the minimum theoretical breaking length you need for an untapered cable just to reach GEO without breaking,
I have a feeling this number is going to be big.
it's immense. The requirement is 4,960 kilometers.
4,960. Compared to Kevlar's max of 400, we're not even in the same ballpark.
Not even close. We're short by a factor of 12, even with our best current materials. And this is where the concept of the taper ratio becomes absolutely critical.
Because we don't have that super material, so we have to use geometry to make up for it.
Exactly. As Pearson established, the cable can't be a uniform thickness. It has to be thickest at GEO, where the tension is greatest, and then taper dramatically toward the ends. The taper ratio is just the ratio of the area at GEO compared to the area at the anchor.
So walk us through the math here, because the numbers are just, well, they're literally astronomical.
They are. If the specific strength is too low, the taper ratio becomes exponentially large. So let's take steel. The required taper ratio for steel is 1.6 times 10 to the power of 33.
A non-Ilian. That's a number that doesn't even feel real. You'd need a cross-section at GEO that's 1.69 million times thicker than at the surface.
It's scientifically unfeasible. Even using Kevlar, the ratio is still 2.5 times 10 to the 8, or 250 million. The total mass of the material is just impossible.
So doesn't that make the entire concept dead on arrival until that fiber exists? Are we just talking about science fiction dressed up as engineering?
That is the core debate. And to make it feasible, engineering studies calculate we need a specific strength approaching 48 megapascals per kilogram per cubic meter.
Which is a pretty abstract unit for most of us.
It is. So the International Space Elevator Consortium created a more accessible unit, the Yuri, named after Artsudanov.
A Yuri. So what do we need in Yuri strength?
A functional Earth elevator requires a tether of 30 to 80 megayuri, which corresponds to a breaking length of about 3,100 to 8,200 kilometers.
Okay, so that's getting into the right territory.
It's getting closer. And this is why, after conventional materials failed, all hope pivoted to nanotechnology, specifically carbon nanotubes.
Because carbon is super light, and the theoretical bond strength of the atoms is immense.
Exactly. CNTs seemed like the perfect solution. Edwards' design back in the early 2000s assumed a material with a specific strength of 77 megapascals per cubic meter, a number only CNTs seemed theoretically capable of meeting.
But that dream has faced a massive reality check.
A huge one, moving from theoretical possibility to manufacturing impossibility. The problem is that while tiny lab strands show immense strength, that integrity just plummets when you scale it up.
All about atomic perfection, right?
It comes down to that. For a CNT to reach its full strength, its hexagonal lattice structure has to be absolutely flawless. Even one single atom out of place creates a defect that drastically decreases its tensile strength.
And the practical manufacturing challenge is still completely unsolved.
Critically so. This is why Google X shelved their project. They realized that no one has ever manufactured a perfectly formed, structurally sound carbon nanotube strand longer than 1 meter.
1 meter. And we need a 100,000-kilometer cable.
It's a huge gap. But the quest for the perfect fiber hasn't ended. Researchers are now focusing on other nanomaterials.
What are the new contenders?
Things like boron nitride nanotubes, which are similar but more stable, diamond nanothreads, which were first synthesized in 2014, and the latest focus of the IAA studies is macroscale single crystal graphene.
So the consensus seems to be that we just have to wait for a revolution in material science on Earth before we can even begin talking about construction.
That's the hard truth. The physics are sound, the engineering concepts are mature, but it all depends on that flawless, ultra-strong fiber existing first.
Okay, so let's assume for a minute that material science delivers. We get a ribbon of 80 megaUri strength. Let's pivot to the infrastructure you'd need to actually deploy and operate this thing, starting with the base station.
Right. Modern proposals favor highly sophisticated mobile base stations, usually large ocean-going vessels or platforms anchored near the equator.
And what's the advantage of having it be mobile? A fixed structure on land seems simpler.
Mobility provides a couple of crucial advantages for safety and operation. First, it allows the base to maneuver to avoid atmospheric hazards like hurricanes or severe storms.
Which would put huge lateral stress on the tether.
Catastrophic stress. And second, and this is maybe the most critical part for long-term survival, mobility allows the anchor to dodge trackable space debris.
Right, because the tether is a massive navigational hazard.
It is. So the mobile anchor can slightly shift the cable's position over time to avoid predicted collisions. It's essential to prevent a catastrophic cut. And third, you're in international waters, which simplifies the immense geopolitical challenge of it all.
Okay, so the cable is anchored. Now, the transport vehicles, the climbers, how do they actually move up a 100,000-kilometer ribbon?
For the thin, ribbon-like cables, most designs use friction rollers to grip the ribbon. They're basically just electric-powered machines climbing a vertical road.
And throughput is critical for the economic case. How fast are we talking? This isn't a quick trip.
No, it is not. The speed is limited by power, the cable's thermal tolerance, and those Coriolis forces. Even at a very fast rate, say 300 kilometers per hour.
Like a high-speed train.
Exactly. The transit time to GEO would still take about 5 full days.
5 days of straight vertical ascent. Which brings us to power. How do you power a vehicle for that long over that distance?
That's one of the biggest engineering challenges after the cable itself. The currently favored method is laser power beaming.
Which sounds like pure science fiction.
But it's solid, cutting-edge engineering. You have megawatt-powered lasers on the ground, shining a highly focused energy beam up to a photovoltaic array on the climber. The array converts that light into electricity to run the motors.
What are the hurdles there? Beaming megawatt power through 35,000 kilometers of atmosphere.
Several huge ones. First, atmospheric absorption and scattering. Clouds, humidity, turbulence, they all sap energy from the beam. Second, you need incredibly precise targeting and adaptive optics to keep that beam focused on a tiny moving target tens of thousands of kilometers away.
And the energy requirement must be staggering. Are you powering a small city for one launch?
For a large 20-ton climber, yes, the power input could be in the range of 10 to 20 gigawatts. The output of a dozen large nuclear power plants focused purely into that beam.
Wow, okay, let's talk safety again. A 5-day transit means a lot of exposure to the Van Allen radiation belts.
That is a severe and often understated concern for passenger travel. That prolonged exposure means you'd need significant shielding for any humans on board.
And that shielding adds mass. Does that destroy the economic advantage?
That's the perfect critical question. For human passengers, yes, the added mass of shielding absolutely decreases the payload capacity and drives up the cost per kilogram. It might even push it back towards rocket pricing for human transit. This is why initial concepts are all about cargo.
Right. And finally, the counterweight. The big balancing act. What are the options?
3 main options. You could use a captured near-Earth asteroid. You could build a large, purpose-built space dock or station out past GEO. Or, the simplest option, you just extend the cable itself further upward and attach mass to the end.
And extending the cable gives you that huge bonus application, deep space launch.
It's the ultimate feature. Extending the cable far beyond GEO turns the upper segment into a momentum launch system. A released payload instantly possesses tremendous horizontal speed.
How far can that reach?
If you release a payload from 100,000 kilometers up, it has enough speed to reach the asteroid belt. If you extend it to Pearson's proposed 144,000 kilometers, the velocity upon release is a staggering 10.93 kilometers per second.
That's enough to send probes to Jupiter.
At least Jupiter, yeah. It completely changes the economics of interstellar exploration.
So let's talk dollars and cents. Because the true driver behind investing trillions into a material that doesn't exist is the economic case.
And the disparity is staggering. As of 2022, conventional rockets cost about $12,125 per kilogram to get to GEO.
Which is why space is so prohibitively expensive.
Exactly. Space elevator proponents envision payload prices starting as low as, well, $220 per kilogram, maybe $500 per kilogram to GEO and beyond.
Even if we're conservative and say it's $2,000 a kilogram, that's still a 95% reduction in cost. That doesn't just change space access. It creates entirely new industries that are impossible today.
And that potential for control is why the geopolitical incentive is so high. One proponent said the first country to deploy a space elevator would have a 95% cost advantage and could essentially control all future space activities.
But those low cost per kilogram figures, they have to be tempered, right? Trillions to build, the insurance, the operational risk.
They have to be. Those figures often don't include the massive capital expenditure. Realistically, you're probably looking closer to $1,000 or $2,000 per kilogram initially. But even then, the economic advantage is still decisive.
Okay, so how do you even build it? You can't just launch a 100,000-kilometer cable on a rocket.
The key is the spool concept and bootstrapping. You launch a relatively small seed cable on a large spool into GEO using conventional rockets.
And then you unspool it.
Exactly. You pay it out downward toward Earth, while at the same time you pay out a balancing mass upward away from Earth. This keeps the whole system's center of mass right at GEO.
So the initial cable is just a scaffold.
It is. One plan suggests a seed cable that could only support the very first tiny 619-kilogram climber. Then subsequent climbers carry up more material to attach and thicken the ribbon over time.
So the first elevator builds the second, and so on.
Yes, you'd bootstrap your way up to full capacity.
But if the material requirements for Earth are so extreme, are there places in the solar system where this is actually easier to build?
Yes, significantly so. And this is a critical point. The material requirements are much, much lower on smaller celestial bodies.
Let's start with Mars.
Mars is highly favorable. Its gravity is only 38% of Earth's, and it rotates at about the same rate, so the elevator could be much shorter. And crucially,
The materials already exist.
current available materials like Kevlar are already strong enough and light enough to construct a Martian space elevator.
We don't need carbon nanotubes for Mars. The technology is basically ready to go.
From a materials science perspective, yes. Building it would be complicated by the moon Phobos, but the material isn't the barrier.
What about our moon? It's tidally locked, so the centrifugal force method wouldn't work.
That's correct. But you could still build one using differential gravity forces, anchoring it through the Earth-Moon L1 or L2 Lagrangian points.
And again, the material requirements.
Low enough to use existing engineering materials?
So the core takeaway is that the space elevator isn't a single impossible project. It's a spectrum. Earth is at the very hardest end, waiting for a materials miracle. But Mars and the Moon are ready for construction right now.
And that just reinforces that the challenge isn't orbital mechanics, it's manufacturing.
So this deep dive has shown us the breathtaking scale of the space elevator concept. We've covered the elegant physics of that GEO balance point, the angular momentum transfer, that slight westward drag on the planet.
And the transformative economic impact. Shifting space access costs from over $12,000 a kilogram down to maybe a few hundred.
But the entire enterprise hinges on solving that single monumental challenge, material science. We quantify the problem with the taper ratio and the required strength in megauris.
And the International Academy of Astronautics concluded that while it seems feasible, the only thing holding us back is the ability to reliably manufacture flawless nanostructured materials at kilometer scale lengths.
We are waiting for a breakthrough, not in rocket science, but in materials engineering and carbon processing, right here on Earth.
Which raises a powerful question for you, the listener, to think about. We've established that the material required is a flawless fiber, maybe single crystal graphene or a diamond nanothread, 100 times stronger than steel and incredibly light.
So if researchers successfully scale up production of this material, a manufacturing challenge right here on Earth,
what global industry outside of space travel do you think would be the first to be utterly transformed by a material that is effectively unbreakable? Think construction, automotive safety, power transmission, or something else entirely. That's the technology we need to watch, because when that terrestrial barrier falls, the skyhook will be next.